So welcome to this video in which we make a first introduction to sets and subsequently by Thursday we will be discussing the most important part about sets, which is sets operations, and that have their roots in logical equivalence rules that we learned so far. So let's start with the basic definitions of sets. So a set is an unordered collection of objects, just a bunch of objects, a collection of objects. We have no order between them, and this is the main difference with lists or sequence of elements. We will have a section later on when we talk about sequences, and that they have this enumeration nature. So we can talk about the sequence of elements of called A0, A1, A2, etc. As if we have a bijection or a one-to-one mapping between the integers 0 to and so on to the elements of this list, okay, or sequence. But in sets, actually, we don't have this order. We don't have this predefined order on the elements. It's just a collection of objects. So, for example, the students in a certain class. Of course, if we talk about the class list, well, this is a list again, or this is it's like arrays or vectors or a tuple of elements. So we have a certain order between the elements. But if we think about the set of students in the class, so we have no specific order in mind when we think about it. The chairs in a room or any other collection of elements that you can think of. So the objects that you have in the set, they are called elements or members of the set. And the set is said to contain its elements. So all of these elements are they belong to this set. And we use this notation to talk about this relation between the element and the set. It denotes that A is an element of the set, capital A. It's not if A it's not a member of the set A. If the element A, small letter, is not a member of the set A, then we write that A does not belong to A in this way. To describe the set, actually, we can use the roster method where we actually list or cite all the elements that we have in the set. And since it's not an ordered list, it's just an unordered collection of elements. So we could also say that S is equal to A, C, B, D. So although we are using alphabet letters and we know that there is an order on them, but actually S could be represented in any of these formats. So we could also say it's D, A, B, C. Okay, so no problem. You can put any permutation of these elements and you still obtain the same set at the end. So in case you know all the elements and the set is finite, you can use this notation. Yeah, just mentioned that the order is not important and that each distinct object is either a member or not. Listing an element more than once does not change the set. So if you say it's A, B, C, B, C, D, well, it's simply the A, B, C, D set, okay? So again, in sequences, I can talk about this infinite sequence of elements A, B, C, B, C, B, C, and so on, okay? So it's a set, it's a sequence where the first element is A and every other two elements are B, C. Okay, it could be used to denote the protein that we have in a certain DNA. So so again, to represent the DNA, there is a specific sequence in the DNA. So we are really interested in the position of every element. But if you have a set, well, we are expecting just to mention every single element once. If the set is large, then we may use ellipses or three dots to talk about the range of elements starting from a certain position up to a certain end position. It works for the alphabet letters, but also works for integers and numbers or any other kind of ordered set of elements where the order is implicitly known. So other examples, we can use this set to represent the set of vowels in the English alphabet. We can also list all the positive odd integers that are less than 10 to represent all the positive integers that are less than 100. Then maybe we would opt for the use of ellipses. We can also use ellipses at the beginning, actually, to talk about a kind of an infinite lower bound on the set. Sorry, we can also use the abbreviation of the known sets, such as the set of natural numbers or integers, the set of all integers, the set of positive integers, the set of real numbers, positive real numbers, the set of complex numbers, rational numbers, etc. So I think you are already familiar with these sets from previous math courses, and it's no surprise that we are going to use these sets in the upcoming chapters when we talk about functions, sequences, summations, etc. We can also use the set builder notation, where we specify a certain property or properties that all the members of the set must satisfy. And here comes the rule of predicate logic once again. So we can say that S is, for example, the set of elements X, where X is a positive integer that is less than 100. And clearly, predicate logic is a perfect match here because the property is a Boolean property that applies to the elements of the set, and that returns true when it's applied on axes that belong to S, and it returns false for all the elements that do not belong to S, or that belong to the complement of S. We will learn about the complement of sets later on. So how can we do it? So imagine you have, so actually we can write it in this way. We can say that X is greater than or equal to 1, or strictly greater than 0, and strictly less than 100. We can also represent this with predicates, proper predicates. We can say that such as positive of X is true and less than 100 of X is also true. Okay. Yeah, so usually we abbreviate it in this way, but imagine whatever the property that you want to define, well, you can define it as a predicate and just apply it on the elements of your set. And then we will be able to really take any X in whatever universal domain U, where the set S is a subset of U, of this universal set. And then we can actually categorize your elements X into either belonging to S if these predicates return true for those X's, and X does not belong to S if those return false, actually, when applied to your elements X. Okay, good. So let's check this with examples. I think by the end of the slide, we will reach a couple of examples talking about predicates. I just wanted to draw your attention from the beginning that when we define a property, it's rather a Boolean property. Another example, we can define O to be the set of elements X, typically integers X, such that X are odd positive integers less than 10. We may also use this definition here, so we can also restrict the domain at the beginning and then further restrict it with the properties that follow this vertical bar that we pronounce such that or such as. So typically such that. Okay, more examples. Sorry. Positive rational numbers can be defined as follows. So the set of real numbers that can be written as a fraction p over q for some positive integers p and q, and we can also add to it that q is different than 0. A predicate may also be used as follows. So S can be defined as a set of elements X, such as the property P of X or the predicate P of X is true, as I said at the beginning. And then a typical example could be the set S with elements that are actually prime, such that the prime of X is true. We can also use the interval notation. So it's sometimes useful to use the brackets to denote closed intervals and parentheses to denote open intervals. We can also use the fully open interval to denote the elements that are strictly greater than the lower bound. Here it's A, and strictly less than the upper bound, which is B. Maybe you noticed that I'm going somehow quickly on these notions, but because I'm so confident that you're already familiar with them. So it's just a refresher on sets. So please allow me to go quickly on these basic notations and concepts. And whenever there is an important information that I want you to dig deeper on, I will absolutely stop and ask you to pause the video and to think about it. So often when we talk about a certain set, or eventually when we learn about operations on sets, when we have certain relations between sets, we will use a famous representation of sets as bubbles, and then we show in a 2D space the correlation between sets, whether the sets have some elements in common, whether they are disjoint, they have no elements in common, and we can also talk about the elements that do not belong to those sets. So usually with the Venn diagram, where we draw a square or a kind of a rectangle to denote the set of all the elements under consideration, the set that we call the universal set, we start drawing bubbles inside that universal set for our subsets that are under consideration. And as I said, in a 2D space, we can show the correlation between these sets. So whenever you have a certain problem that you are thinking of, well, you always have this universal set that contain everything currently under consideration. So suppose we have a certain problem where we are reasoning about the students who are taking a certain course, students who are registered in another course, and so on. So maybe the universal set could be all the students in a certain major, in a specific major, or all the students in the whole college, or all the students in Lebanon, or in higher education, particularly, or let's say all over the world, or the universe. So you can enlarge your universal set as much as possible, but so often it's sufficient to stop at a certain level that where actually that set, once it contains all the sets that are currently under consideration, then you can stop and you can consider it as your universal set. Can't we talk about the universal set that contains everything? Actually, no, because of the very nature of sets, you will see in a few slides we can put sets inside each other. So we can talk about a set of elements where the first element is the set 1, 2, the second one is 2, 3, and the third element is just 4. Okay, so yeah, since we can nest sets once inside the other, so this never ends because Now I can create a bigger set that contains this one with other stuff, okay? And I can put it in another set and so on and so forth. So it never ends. So I can put a set in which this U exists with other U's and other sets and other elements. So it, it, it never ends, and that's why we cannot talk about the universal set, but you can talk about the universal set containing all the sets under currently under consideration in a specific problem. So sometimes it's implicit, and sometimes it's explicitly stated in the exercises, or you specify it yourself when you define when you are tackling a certain problem, and the contents depend on the context. There is the extreme, on the other extreme, there is a very particular set called the empty set that denotes the absence of any element. This is why we use a very particular symbol for it, this phi symbol. But also know that this symbol is also used, the empty braces. I feel sometimes that student may get a certain confusion with this empty braces symbol once you have very multiple empty braces that are nested inside each other. So to denote the empty set with a particular symbol is really helpful to quickly understand the elements that are constituting certain sets. I already talked about the Venn diagram, so named after John Venn and from Cambridge, UK. So it's a visual representation, 2D visual representation of sets in which we represent the universal set using a rectangle, and the sets inside the universal set with ovals. So for example, we can consider the set U to be the set of all English alphabet letters, and then V to be the set of vowels. Clearly, V is a subset of this universal set, and precisely it's a proper subset because we are sure that there are some elements such as X and the letter Z and the letter B that actually belong to the set U, but they do not actually belong to the set V. Okay, so we know more about this set relations, this subset relation between sets in a couple of slides. Yeah, something to remember is that the fact that you can nest sets inside each other. Actually, you can have a set composed out of these four sets, for example, or a set containing this set and the letter A, and this set containing the letter B and C. So if you ask me about the number of elements in the outer set, I would say there are three elements in that bigger set. The first element is this set here, 1, 2, 3. So this set itself, or this element itself is a set, and it has also size 3. It has the three elements in it, 1 and 2 and 3. The second element is just a simple element. It's A. Except if you come and tell me that this letter A represents another set one day. But from what I see, it seems a simple element. And then the third element in this big set is also a set. Okay, it's like the concept of having bags containing other bags containing elements in them, and of course you can have some elements outside of the inner bag and just inside the outer bag. Okay, if you think about it in this way, then you don't find it that surprising. Clearly, the empty set is different from the set containing the empty set. Okay. Also, in a couple of slides, we will talk about the cardinality. I just evoked the concept very quickly in this example here, and I talked about the number of elements in this set. So in a couple of slides, you will see that this set here the empty set is by definition considered to be of size 0 because by definition it contains no elements. But this set here that contains the empty set has size 1, okay? And actually it has one element in it, which is the empty set. So you can also think about it in terms of bags, and actually this um, outer bag actually contains an empty bag in it. Okay, so it's no more empty. This outer bag is no more empty because it contains something. It contains an empty bag. Okay, while this one inside is empty. Okay, so clearly, once you visualize it in this way, you find it quite intuitive. Okay, so let's have a couple of words about the set relations and then later on about set cardinality and Cartesian product of sets. So we have two operators that we would like to talk about today, which are the set equality operator and the set and the subset relation between sets. So two sets are equal if and only if they have the same elements. We write in this case that A is equal to B. And we write it only if A and B are equal sets. It means they have the same elements. Well, actually, logically speaking, this means that for every element in the domain U, okay, that we have currently under consideration, if X belongs to A, then necessarily X must belong to B, and vice versa. If X is an element in B, then necessarily X must also be in A. So this depicts actually this reality. If you have these elements here in A, then clearly all of them also belong to B, okay? And if you consider any element in B, then it's also an element in A. So these two sets actually, they are the same, okay? You will see that this has something to do with also the subset relationship between sets that you're already familiar with it. And we will see that this means that A is a subset of B and B is also a subset of A, okay? We'll see it in a couple of slides. So an example, these two sets are actually equal, okay? For example, the set of even numbers, okay? Let's call it E. Actually, we cannot bind it because it's, you will see later on when we will talk about cardinality of sets that this is an kind of an infinite set. Um, but yeah, just assume that we can give it this name. So maybe yeah, without the Venn diagram, let's just call it E, the set of even numbers. Well, this is clearly equal to the set of elements of the form X, such that there exists a K belonging to the set of natural numbers, and such that X is equal to 2 times K. Okay, well, just because this is the definition of the set of even numbers, okay? So this set and that set, they are equal. And by the way, the one to the right is the sole definition of the name that is given here to the left-hand side, okay? Um, Good. So here you also have another example. So they are just, in the first one, they are showing you that the order does not matter. And then the second one, they are really showing you that the repetition of elements does not change the nature of the set. Well, a particular case of the equality is the subset. Or on the contrary, actually, it's a particular case of the subset relationship is the case of equality. But in general, sometimes all that you can say about two sets is that every element in the first one is an element of the second one. But maybe you're not yet sure about the second part of this reality. You're not sure about the bidirectional. Okay, so if you only have this part of the reality, if you can only prove this part of the bidirectional, it means only this implication and not the bidirectional, then in this case, all that you can say is that A is a subset of B. Okay, so it's a subset or equal to B. We are not yet sure. Okay, we cannot confirm actually, and but we cannot also neither deny it completely or refute it. We have to think about it. We have to prove it. We have to just take one element in B and check whether it is necessarily in A or not. Okay, and only then we can say something about whether A is a proper subset of B or not. Okay, or whether A is equal to B. So the definition of a subset is, as stated here, it's when every element of A is also an element of B. It's denoted in this way, and it holds on if and only if for every element X in the universal set that contains both A and B. If X belongs to A, then necessarily X belongs to B. One, let's say, side effect of this definition is that the empty set would be considered a subset of any set. Okay? Well, why? Because no matter what the element that you consider, if X belongs to the empty set, then necessarily that element X, that element X belongs to any set S. Okay, so we can also add for every S, or we can simply say that we have this for any arbitrary set S. Okay. So why do we have this implication true? Well, because the premise is always false, okay? By definition of the empty set, no element belongs to it, okay? So by definition, to prove this, no matter what you consider as an element X in whatever universe is said, that element X be, belongs to phi is false in the first place. Okay, so it's not the case that X belongs to phi. Okay, and hence you can entail from this whatever you want. For instance, you can entail from this that that X belongs to that element S, and this is why. So just as a reminder, just in case you forgot about it, P implies Q is true whenever P is false, or if P is true, then necessarily Q must be true. Okay, but if P is false, then actually the implication is always true. No matter what the conclusion is, no matter what Q is. So yeah, this is why, by definition, and according to the definition that is given here, clearly the empty set is a subset of every set. Yep. What else? So I think we answered these question already in the discussion, and we also have another side effect is that every set S is a subset of itself, because if you pick up any element in X and S, well, you will find it also necessarily in S itself. Okay. By the way, any set is equal to itself because you can also add the bidirection. But just in case you would find such a situation, well, you can safely say that the set is a subset of itself. When would you use this? Well, sometimes when you're doing the entailment and the reasoning on sets and their relations, you may need to use this fact. Okay, so you don't have to prove it, just take it for granted. In the best case, refer to slide number 13 here. To show that the set is or is not a subset of another one, um, well, we show that if X belongs to A, then X also belongs to B. So we start from the premise, and then we show that the conclusion X belongs to B is necessarily true. Okay, so we show that for an arbitrary element X, this relation or this implication holds between the two facts, X belongs to A and X belongs to B. We can also show the contrapositive of this one. So we can show that for every X, if X is not in B, then necessarily X is not in A, by the way. Okay, so these two implications are equivalent. To show that A is not a subset of B, well, in this case, it's sufficient to find a counterexample. So if you want to show that it's not the case that for every element X, X belongs to A implies X belongs to B, then it's sufficient to show that there exists an X such that not this implication, okay, and not this implication means that X belongs to A, okay, it's P and not Q, okay, so not P implies Q, remember, it's not P or Q, which is P and not Q. Okay, so it's P and not Q. So that's why we should just show a counterexample. We should show one element that belongs to A and does not belong to B. Okay, or we can also write it as not X belongs to B. Okay, guys. So it's really fantastic to see how the rules that we learned about the negation of quantified about quantifiers or quantified predicate logic expressions, how it works wonderfully here, and it gives us a very intuitive result because, yeah, it's a key to show when you want to show that A is not a subset of B, it is sufficient to come up with a certain element that belongs to A and does not belong to B. So this is really quite intuitive, okay? So we could see it from the beginning, but it's just nice to see that the negation of this one is equal to this expression is equal to this logical expression, and to see the beauty of the logical formalism, including for negated quantified expressions. So in this case, as we said in the part related to proofs, we would be providing a counter example to claim that X belongs to B implies X belongs to A implies X belongs to B. And let me just discard these annotations and then jump to this part here. So example, the set of all computer science majors at your school is a subset of all students at your school. And the set of integers with the squares less than 100 is not a subset of the set of non-negative integers. Okay. Yep. So let's have another look at equality of sets now. I drew your attention to this earlier. So recall that two sets A and B are denoted with this symbol, and it holds if and only if for every X, X belongs to A is equivalent to the fact that X belongs to B. And using logical equivalences, we have that A is equal to B if and only if for every X, X belongs to A implies X belongs to B, and X belongs to B implies that X necessarily belongs to A, which is equivalent to A being a subset or equal to B, and B being a subset or equal to A. And you cannot have both unless you have A equal to B, okay? And vice versa, actually. So, but sometimes you can show that a certain set is a subset or equal to another one, but that they are different, okay? Well, in this case, you can say that A is a proper subset of B. Okay, so you can show this. Let's see it with a Venn diagram. So if you have A here and you have B there. Okay, so they don't have the same circumference, the same frontier. Well, maybe uh, they don't, because you have certain elements that are here in B. Okay, so these are B elements, and B1, B2, B3. And inside A, you have the AB elements, okay, AB1, AB2. So these are elements of both A and B at the same time. Okay, so in this case, um, you can show that for every element in A, so you can write that A is a subset of B, because for every element in A, that element must necessarily be an element of B. But you end up having this inequality and this proper subset relation, most probably because you could find a certain element in B, okay, such that that element is not an element in A, okay? So if you could find such as those BIs here, if you could find certain elements, some elements in B and that are not in A, well then most probably in this case, this means that actually B is not a proper subset of A, and clearly in this case, B is different than A. And but since in the beginning we had A is a subset of B, then we can safely say that A is a proper subset of B. Okay, so we cannot say this until we prove this implication, and we cannot say this until we prove both the first implication and the second existential formula. Okay. So for the second proper subset, you need actually both, okay? But for the first one, you need only this one here, okay? So this is formula one, this is formula two. Formula one is sufficient to say when you have one, you can say this formula, the subset. But to show that A is a proper subset of B, then you need both one and two, both of them. Okay, so you have more information about A and B now to be able to say that A is a proper subset of B. Good. Well, I think the remaining are simply details and a diagram as I did. Well, one last notion about sets that we want to mention in today's lecture is set cardinality, or the size of sets. So if there are exactly n distinct elements in S where n is a non-negative integer, then we say that S is finite. Otherwise, it is infinite, and we will have a whole session about the cardinality of sets later on, after we talk about functions um, um, in a couple of sessions later on. So the cardinality of a finite set is denoted by vertical bar A, um, vertical bar. So it's the number of distinct elements of A. Examples. Well, the empty set has size 0 because it has 0 elements in it, no elements in it. If S is the set of letters in the English alphabet, then the size of S is equal to 26. And if your set is the set containing the elements 1 to 3, then the size of it is equal to 3. The size of the set containing the empty set, that one is equal to 1 because it contains one element, which is the empty set. And the set of integers, of course, is infinite. Um, another concept about sets is the power set. So it's the set of all subsets of a certain set, okay? And we denote it by P of A, typically calligraphic P of A, okay? But in this course, it's fine. We distinguish it easily with a simple capital letter. So it's called the power set of A. And if for example, this set is the set containing the two elements A and B, then the power set of A, you see the calligraphic P once again. So it's the set containing all the subsets of A. Well, the empty set is one of these subsets. The set containing the element A alone is a subset of A. Okay, can't we say that this is a subset of A? Well, of course. Can't we say that the empty set is a subset of A? Well, of course. Can't we say that this one is a subset of A? Absolutely. And that one, because every set is a subset of itself. We already discussed this, okay? So, and there are no other subsets of A, okay? Um, so this is why this power set of A is this set here. Good. In general, if a set has an element, then the cardinality of the power set is 2 to the power n. We will have actually a proof for this in chapters 5 and 6 when we talk about induction and counting, okay? But just very quickly, if you check the composition of this subset of A, it's as if you have, let's say, suppose you have the elements A, B, C, and you want to check all the possible subsets from them. Well, the empty set would be equivalent to the fact that neither A is present, nor B, and neither C. Okay, as if we are building a truth table where we are putting false in below a certain element if it is not present in the subset that we are trying to build, and true whenever this element is present. So, okay, do you see? So, for example, the true that you have really at the end is equivalent to the set A itself. Okay, so here I'm considering another A, an A that contains these three elements, A, B, C. The TFF is for the singleton set that contains only the element A. FTF is the singleton set that contains B. The FTT, for example, that you have somewhere is equivalent to the set no A, so you don't have A in it, but you have B and C, okay, etc. So, okay, the last one, which is equal to A, is the set containing A, B, C. And you know it already from our work on the truth table. You know that the size of this table would be, if you have n propositions, then it would be equal to 2 to the power n. Okay. So, for example, in case of three elements in the set, the total number of subsets would be equal to 2 to the power 3, which is equal to 8. Just enumerate them, pause the video, enumerate them, and make sure by yourself that this is true. Great. Sometimes we want to define a certain order on the elements coming from a certain set or multiple sets. So to do so, we use this parenthesized notation. And we talk about, in this case, about ordered tuples of size n or of arity n. So we use parentheses and we use commas to separate these elements. So it's the ordered collection that has A1 as its first element, A2 as its second element, and so on until AN. Well, this is clearly quite similar to what you used to call list or vector or table or array in programming languages. Okay, so and this is what we have in memory, because the memory addresses are kind of sorted or kind of enumerated, numbered, and this is why when we allocate a certain variable in a certain memory space, and then we allocate another one right after it, and so on and so forth, in order to create an array or a vector, well, then we can talk about a list of elements or a tuple. Um, Two n-tuples are equal if and only if their corresponding elements are equal. So the, it should be uh, um, the same element at the same position. And of course, we can have the same element repeated at multiple places, no problem. So two tuples are actually called ordered pairs or pairs of elements. And as an example on the equality of tuples, the tuple AB and CD are equal if and only if A is equal to C, the first element in the tuple is equal to the first element in the second tuple, and the second element of the first tuple is equal to the second element in the second tuple. Okay, and B is equal to D. Good. How can we create tuples? Well, there is a certain operation that we can apply on sets that we call the Cartesian product. Um, um, First studied by René Descartes in the 17th century. So a Cartesian product of two sets is denoted by this times operator. It's A cross B, pronounced as A cross B or A times B, typically A cross B. And it's the set of ordered pairs AB, where A belongs to A and B belongs to B. So it's the set of ordered pairs where the first element belongs to the first set and the second element belongs to the second set. Well, why would we define Cartesian products? Well, it's quite recurrent in problem solving in general and algorithm design in particular to use a finite set of elements to denote the set of possible assignments of a certain variable. And sometimes your solution is, rather than being a subset of a certain set, is a Cartesian product. So suppose you have a set of employees, E, and that is equal to three employees, E1, E2, and E3, and you have a certain set of jobs or tasks. Okay, so a job, let's say number one, job number two, um, job number three, and then job number four or task number four. And imagine that you have to assign those jobs to those employees. Well, of course, you have plenty of possibilities. It depends on the constraints, on the expertise of every employee, etc. But it's just good to know what are this total set of possibilities that you have, so that you can know the upper bound and the most naive, exhaustive brute force algorithm that you can write to check all the possible solutions. So actually, no matter what your program would do, it would come up with a certain solution to be a subset of this set here, to be a subset of the set of uh, um, uh, possible tuples or a pair of elements of the form EI job K, okay, where EI belongs to the set of employees and job K belongs to the set of jobs. And actually, this pair denotes that the job K is assigned to the employee EI. Okay, so your final solution would be a certain subset of this set of elements. Okay, I'm really sorry for those horizontal lines. It's horrible, but I'm not sure why my pen is doing this on particularly on PowerPoint. So yeah, let's learn more about these annotations. So it's can be defined in this way. It's the set of pair of elements or a list of elements AB such that the first one belongs to A and the second one belongs to B. Um, sorry. So Example, if A is composed out of these two elements, A and B, and capital B contains 1, 2, 3, then the set of possible pairs of A cross B would be equal to A1, A2, A3, and B1, B2, B3. So you'll ending up having 6 different elements. And this is also a noticeable um, uh, um, um, remark is that actually if the size of A is equal to certain value n and the size of B is equal to a certain value m, then the size of their Cartesian product is equal to the product of their sizes is equal to n times m. Okay. We will use this property actually later on in the chapter corresponding to counting, so just keep it in mind. We can generalize actually the Cartesian product to multiple sets. If you have n sets, you can create n tuples by combining elements coming from those sets, okay? And the set of all the possible tuples that you can compose out of all these sets is the set A1 cross A2 up to AN. It's the set of all tuples of this form, okay? So it's equal to the set of all the tuples of this form where every AI belongs to the set capital AI for I equal 1 to n. Example, if A is equal to 0, 1, B 1, 2, and C is 0, 1, 2, then these are all the possible set of elements. Clearly, the size of the set would be equal to the size of A times the set of B times the size of the set C, okay? So which is 12 elements. So that's it for this time. Next time we will talk about set operations, which you already know also most probably. So namely the intersection of two sets, the union and the complement of a certain set. And then we will see how close these operations are to the and or and not operators that we learned in logic. And hence we will generalize this to the XOR. And we also talked about the implication and the equivalence and their correspondence to the subset and equality between sets. So more about these in the next lecture on Thursday. See you then.